Hello, everyone. Welcome to this webinar called Wolfram Language for Python users. My name is Dimitar. I work at Wolfram Research Europe as a technical content writer. And today I'll be talking to you about, both Wolfram Language and the Python language. Two really nice, really cool, really useful high-level languages. And we'll be comparing, well, we'll cover how to use Python from Wolfram Language, and we'll do the other way around as well. We'll be using Wolfram Language from Python, for which will be the second half of the webinar will live mostly in Jupyter notebooks, whereas for the first half of the webinar will be in um, in Wolfram notebooks. Okay, so before I start and while I'm introducing the content and the plan for today, I'll shoot off a few polls for those of us watching us on Big Marker. There are just some questions about your usage um, of Wolfram Language, and it helps us really tailor the upcoming content for you. So, okay, while you're answering that, let me just give you a brief kind of introduction on what we are going to be covering today. We'll start obviously with an introduction of both languages and a brief history. When were they developed? Kind of what was the vision of their development and what do they look like today? Then we'll cover some similarities, differences, code structure, so differences in terms of code syntax, code style, and so on. Then we'll look at what are the main advantages of each language. So obviously they're both general programming languages. So theoretically speaking, you could achieve anything using either language. But obviously there are some things that are much easier with some languages than others. So we'll be covering that topic in relation to both Wolfram Language and Python. And then we'll look at some examples. So we'll look at how the same example is written in Python and how the same example is written in Wolfram Language to give you kind of a more practical feel of the differences, especially in syntax of both languages. We'll have some examples of calculus, kind of core base library language stuff, functional programming, data analysis. And then we'll move on to actually connecting the two languages together. So we'll look at how to call Python from Wolfram language environments, in this case, a Mathematica notebook. So we'll be using external cells. We'll be starting external sessions kind of more programmatically. And so on, just different ways of using Python from Wolfram language. And then, as I mentioned in the second half of the webinar, we'll live in some Jupyter notebooks and we'll be writing Python code, but we'll be calling in Wolfram language for some more specialist things, if you will. Cool. So that's a brief summary of what we'll be covering today. So let's get into it. And before I get into it, I just have one more poll. It's about your experience with Python. I'm especially curious about that because since we'll be covering kind of both languages, knowing whether the audience today is very experienced in Python or not at all experienced in Python, but curious, that will kind of help me to decide which parts to focus on in this webinar. So if we have people who are not that experienced in Python, I'll spend a bit more time on setting up, for example, virtual environments and setting up your Python workspace and other things that are kind of the most common stumbling blocks when people are trying to start out with Python. On the other hand, if everyone here is a Python expert, then I'll probably linger a bit longer in the Wolfram notebook and show you as a Python user what you can, the benefit you can get out of the Wolfram ecosystem. So I'll let that poll run. Feel free to respond with kind of your proficiency level in Python, and I'll try to tailor the session to the audience, so to speak. Cool. Let's get into it. So here are some basic questions that we'll be covering in the webinar. I'm not going to go through all of them because we're going to cover them in the webinar anyway. So let's get into it. Brief history of both languages. Python first published in 1991. object-oriented language, meaning that everything in the language is an object, um, and also quite well known for using notebooks, the notebook format that I'm sure you're all familiar with, where we are mixing normal text or marked up text with computer code and outputs and images and interactive elements and so on. The in the Python environment, I believe the most widely used notebooks are Jupyter notebooks, and this is what we'll be doing in the second half of the webinar. They were inspired by the Mathematica notebooks that you see on the screen now. Mathematica, kind of a similar history in a sense. So it was first released in 1988, so a bit older than Python, but both languages have been around for a very long time. They are very mature languages. They're widely used for different things. Mathematica is typically a combined kernel. So Wolfram Language is the actual programming language that interprets Wolfram Language code, and Mathematica is the front-end notebook interface. So typically nowadays we use Wolfram Language and Mathematica interchangeably, but that's kind of the technical difference between them. But the vision of Mathematica since the beginning, really, since the founding of the language, has been to provide a full stack experience, if you will. So not only the interpretation of programming code, but also the interface to make working with programming code easy, intuitive, and pleasurable. In terms of key strengths, symbolic computation is something, again, at the very core of Mathematica since the beginning, and it remains probably the best environment for symbolic computation out there. But as I mentioned, nowadays it really is a general purpose programming language. So you can do much more than symbolic computation. And in fact, I think in this webinar, for example, we only have one symbolic computation example. All the other examples are doing other stuff, some numerical analysis, some machine learning, and so on. With both languages, they are interpreted languages. So all you need to do is send a text file, of the code to the interpreter, and it's going to give you the result. So as such, you can use Wolfram Language and Python from any, well, not any, but there's high-level support for the most popular IDEs such as VS Code, IntelliJ, Eclipse, and so on. Cool. Some more similarities and differences. I'll try to get through those quickly because I'm kind of eager to get into the code. But both Python and Wolfram Language are low preamble interactive languages. That's probably the biggest similarity between both languages, is that they are very easy to get to. There is very little boilerplate needed to get started with either language. You just go in and you start typing the commands, the functions, and you can get the results much faster compared to some lower level languages, such as Java, C, Rust, what have you. Both languages focus on computation, support science, and mathematical concepts. Again, Mathematica, that's at the very core of the foundation. Python has become extremely common in different scientific fields. Both support a number of IDEs, we mentioned that. They're both considered multi-paradigm high-level languages, I mentioned that as well. Allow for code delivery in multiple forms. So this is mostly about notebooks, where we have these interactive documents that contain text, narrative, and computer code. Don't require memory management or compilation for most applications, even though we are currently working on the Wolfram compiler, which for those people who are interested in compiled code to really squeeze out the maximum benefit of their hardware, we are working on that as well. But both languages, both Python and Wolfram Language, are interpreted, so you don't need to compile anything to run code. You just need the interpreter. So let's get into some differences. Python, obviously, the biggest difference is that Python is an open source language developed by members of the community. It's free to download, it's free to use, it's free to do, it's free to change, it's free to do whatever you want with it. On the other hand, Wolfram Language is a single source language developed in-house at Wolfram Research. It operates on a licensed business model, so if you want to use the language, um, you need to get a license from Wolfram Research where the language is developed. And so that's a massive difference, right? There's no way around it. So it's a massively different business model, and ultimately there are trade-offs that come with each business model. So the benefits of let's say of the open source nature of Python is that it has a very thriving, very friendly, very active online community. There are millions of Python users in the world, and if you're looking to do something, there's a huge chance that that some Python developer will have developed a solution for the problem you're facing. So that's the good side. The negative side of that is that because there is no single entity managing the language, you get a lot of issues with trying to glue code from different sources. So it's a very common experience. I'm sure Python people who are experienced in Python can attest that it's a very common experience when you're trying to combine several libraries. Let's say two different libraries. Very often you're working with way more than two libraries together, and each one has its own kind of style and syntax and even philosophy in some cases. So you often find yourself writing kind of the connection or the glue between different libraries, and it can be frustrating at times. And again, depending on what you're doing. There are issues with documentation as well. For example, somebody has written some really cool Python library that does exactly what you need, but the documentation is so sparse, if it's there at all, or it's so badly written that you cannot figure out how to use it. So there are things like that that are the kind of the flip side of the open source nature of Python. Whereas for Wolfram Language, the benefit really is that because it's developed by a single entity, we have, even though we have thousands of functions in the language already, so you don't need to rely on external libraries. Everything is included, and everything works nicely together. So we'll have some examples later on, but we always try to make the output of one function play nicely with the input of other functions and so on. So everything is meant to be to really feel like you're working in the same environment. So that's the positive. The negative, obviously, is you have to pay money to use it. So and that goes to the development of the language and so on. So very different visions, very different philosophies of both languages. As I mentioned, ultimately it is a trade-off between different things. And really, this webinar, what we're talking about today, is to make use of both. So to get the best out of both worlds, to combine the advantages of one language with the advantages of the other. There's no need, as a programmer or as a researcher or somebody who is interested in coding in general, there's no need to only use one language religiously. In fact, you should combine different tools, different paradigms, different languages together. And that's what we're going to be doing here. This is just a broad comparison between the built-in functions between Python and Wolfram Language. This is since 13.1, so we'll probably have added a few hundred more because we are now on 14.3. But this really illustrates the difference in philosophy between the two languages. With Wolfram Language, you get everything packed into the language. Maybe not everything, but at least 6,000 things packed into the language. And really the aspiration is that whatever a person might try to do, whatever question they're trying to answer, whatever method they're trying to employ, that they will have what they need inside the language. Whereas with Python, the philosophy is that it's an open language, and if you need to do something, you can you can find an external resource written by somebody who is an expert in that field, and then you can just use the language primitives to kind of glue that solution together. So very it's very interesting to kind of observe how different languages take different approaches and different philosophies. Let's get into some actual code. So here, what you're seeing on the screen is a side by side of a simple kind of workflow that determines um, whether a number is a prime. So on the left hand side, you see the Python code. Uh, Obviously, that's just one possible way to write that code. You can write it many different ways. And on the right hand side, you see the Wolfram language code that is basically a line by line translation of the Python code on the left, which is not always the best way to write code, and in fact, it's rarely the best way to write code. But in this case, it illustrates some syntactical differences, mostly between the two languages. So you can see things like square brackets in Wolfram language are normal brackets in Python. You can see if statements. Print is always print, if is always if. There's an explicit else in the Python code, whereas in Wolfram language, the last statement is else, and so on. So kind of a minor syntactic differences in that sense. But the main point we want to make here is that while you can write Wolfram language code as if it was Python code, so you can take each line and kind of do the equivalent of that line in Wolfram language code. That's typically not how you would do it. As I mentioned, both languages have their own paradigms and their own ways of doing things. So in Python, it's very common to have these control flow, if statements, for loops, print statements, breaks, if else, and so on. Whereas what you see here on the bottom of the screen is a much more Wolfram language way of accomplishing the same thing. So instead of having this control flow with for loops and if statements, you define a function and you overload it to accept different types of arguments, and then you execute that function in a scoped block, and so on. So the main point to make here is that, especially if you are coming from Python into the Wolfram language ecosystem, you will be tempted. You will be tempted to write Wolfram language code as if it was Python, but I encourage you to kind of learn the Wolfram language paradigms, because they really make working with the language much easier. Cool. So out of the box functionalities. Again, this touches on a difference that we were just talking about, the difference in philosophy between having everything included in the language and having to rely on external libraries. And you can see that with Wolfram language. So what we're seeing here is a bar chart of how many functions existed in each version of Wolfram language. So version 1 already started with 500. We are on version 14 now. We have 6,600. So another difference between between Wolfram language and Python, and it's another difference that takes some time to get used to. If you're coming from Python, is that if you're coming from Python, you're kind of used to writing everything yourself. So when you want to solve some problem, you start thinking, okay, how do I write this function, this control flow, whatever that will help me accomplish a task. So if we go back to the example on the previous slide, you need to check whether a number is a prime. So you write this nice if statement, and you have a for loop inside, and so on. Again, as I mentioned, you could write the same thing in Wolfram language, but one kind of a paradigm difference between Wolfram language is instead of immediately going to write your own solution, check the documentation check the documentation to see whether a function already exists. So again, that's a quite a big quite a big difference in how you think about solving problems. And I found that myself because I had been using Python before I started using Wolfram language. So I do have that perspective of somebody who comes into the Wolfram language ecosystem from another environment, and it was always many times I found myself in the middle of writing some complicated function or some control flow that will help me achieve something, only to find out that there was already a Wolfram language function that does that thing in a much more elegant way. So always do check the documentation. It's very extensive and it's also very well written. Um, so if you are in doubt before you spend 1 hour writing some complicated function, um, just check whether it exists already, because you'd be surprised. Even if you're doing something quite niche, I often find myself um, I'm like, yeah, I'll search in the documentation, but I'm pretty sure that there wouldn't be a built-in function for that niche specific thing I need, and then sometimes there is. So it's always worth checking. um, but to come back to our example about prime numbers, we could write our own logic ourselves, but there is already a prime q um, function in Wolfram language that just takes a number and it gives you true if it's a prime and it gives you false if it is not. Um, cool. Yeah, another thing to mention is that built-in functions, because they are developed by our in-house team, and they are developed by um, people whose job is to develop really efficient, really high-performing programming code. Typically, if not always, the built-in functions are going to be faster than the solutions you write yourself. And you can see our kind of basic custom hand-wrote prime checking function takes much longer to determine whether a number is a prime than the built-in one. Cool. Another difference between the two languages is that with Wolfram language, you have the Wolfram knowledge base built inside the language. So you can ask a lot of different questions about a lot of different real world entities, and you have verified available information right in your notebook. So again, a difference. That's a difference between Python, where if you need some information, typically your first instinct is to source it from the web or from some trusted source and so on. But with Wolfram language, you can for a lot of things you can do you can get the information right from the notebook. And here are some examples with different things you can solve. Obviously, you can solve some mathematical expressions. You can get information about entities like carbon steel. You can get some pop culture information like the Flintstones and Simpsons. You can get genealogical trees or whatever these relational trees are called. Oh yeah, genealogy tree plots. And there really are a lot of built-in entities. The one I think I probably use the most is countries. So if you type something like France, you get the country of France, and now you can query different properties of that country. So let's do the population of France. Get 66 million people. So a lot of information available right away to kind of plug into your analysis. Um, Again, automatically without needing to rely on external sources. Before I move on, let me just show you the syntax for querying the Wolfram language knowledge base. The syntax that was introduced, I believe, a few a few versions ago is this equals in square brackets. So everything you put inside the square brackets will be interpreted as a natural language input and will be matched to the Wolfram language knowledge base. And if there is a match, you will get the information that you ask for. So let's try something: carbon steel melting point, for example. Um, let's see, I haven't tested, but well, it timed out. I think there's something wrong with our servers. But the basic idea is you put any natural language query inside the brackets, and um, you get the information out when the network doesn't time out. um, okay, let's move on to some actual examples of code between the two languages. Um, Here we do have some symbolic calculation um, example, and this example is written in both Python code and Wolfram language code. So it's an integration example, and the problem can be stated as find the indefinite integral of this expression and plot its curve. So here is how to achieve that with Python. We are using SymPy, which is a common library for symbolic computation in Python, and we're using several other libraries as well. We're using matplotlib for the plotting. We'll get a 3D plot out of this example. We're using NumPy for some numeric computation, and I believe this is it. So let's run this Python code, and this is what we get. We get the indefinite integral of this expression, and we have its curve on a 3D plot that we can manipulate and visualize nicely in our kind of new window that matplotlib created for us. So a typical way to solve that kind of problem, and here's the solution at the bottom. A typical way to solve that kind of problem with Python code: just use a library for symbolic computation, use a library for plotting, and then NumPy for your general kind of numeric calculations. As we mentioned, one of the kind of shining points of Wolfram language is its symbolic computation capabilities. So whenever you're dealing with problems like that, chances are that the solution in Wolfram language is going to be much more kind of concise and easy to write and easy to reason with. So in this case, we are doing essentially the same thing as we did in the Python example. And in this case, we're using integrate, which is a built-in function. So we don't need to import any external libraries. And we're using plot3d, which again is a built-in function. And we basically get the same result, a bit nicer looking in this case, in my opinion. But the main advantage is that it is much simpler to do these types of tasks in Wolfram language. So let's talk about some built-in constructs into the language that a lot of people use and a lot of people are familiar with. So in Python, so let's start with talking about anonymous functions or lambda functions, as they're known in Python. So lambda functions in Python are just functions that are not defined as standalone functions. They're written inline, so you can combine some logic right in the line where you need it. You don't need to do the whole define my function, takes arguments, returns something, and so on. So the way it works is you can see the lambda syntax here. You get lambda xy, and you do something with xy, and you return the result. So in this case, we are getting the letter counts for each word in a list. And the list is the following. It has red, blue, and green, and we want to count how many letters each one of those words have. The simplest way to do that in one line of Python code is, we are getting the letter count for each word, and then we are multiplying them all together. So the simplest way to do that is to use a lambda function, and the reduce function, which is built into the functools library. So yeah, as you can see, the solution is a simple lambda function, one line of code, and we get the product, technically the product of the result. That's right. Wolfram language does have a very similar concept to that, and that is the anonymous functions, which use the function syntax, or sometimes you're going to see it as this ampersand symbol. Actually, much more commonly, you'll see it as the ampersand symbol, but let's look at the formal way to write it here. Again, we're doing the same thing. We're doing the same thing as the Python code above. We are counting the characters in each of these strings, and then finally we are applying a function to the result. So we are applying the times function, which gets us the product of all the numbers in result, and you can see we get the same output. Again, one difference is that it goes back to what I was kind of mentioning at the beginning, that in Wolfram language, there's really this effort to make the built-in functions work with everything that they could possibly work with. So in this example, we are using the times function, which gets the product of some numbers. We're using it to some numerical values, but you can just as well apply the times function to colors and get the product of their RGB values, for example. So in this case, we are multiplying the RGB values of this little square with this little square, and so on. Cool. Let's move on to more examples. User-made functions. So again, this is now we're getting into kind of more complete functionality. We're not using lambda functions or pure anonymous functions, or pure functions as they're called in Wolfram language. We are defining our own functions. So let's see what we have in Python. So we have so branching functions are very common in Python. You define a function. Oh, let's go line by line with this Python function. Actually, that would be useful. So we are defining my function one. It takes two arguments. It takes x and c, and it defines some branching conditions. So using an if statement, it says if x is greater than 0 and x modulo 2 equals 0, we are returning something. Then there's another condition. If x is greater than 0, it's returning something else. And then finally, for everything else, we are raising an error. And then we can test that function with some numbers to see what we get. And as we expect, so you can see that in the first example, when we call the function for the first time, we're passing 4 and 2. And you can see that meets the first branching condition. Then we're passing 1 and 2. That meets the other one. And then we're passing -1 and 2. And that raises an error because x is not greater than 0. So we get into this branch. A common way to do the same thing in Wolfram language is slightly different. So instead of defining a function that branches out depending on some conditions, we define a function and we overload it. We overload its definition with different types of arguments. So here we are defining my function one, again, same name, and we are taking two arguments. We're taking x and c, and we are performing some calculations on them. And you can see we're defining the function 3 times. So defining the same function with different argument types is basically what we call overloading a function. And that ensures that if the arguments you pass to the function meet the first definition, then the first block of code will be executed. If they meet this definition, then this block of code will be executed. So it's a much more concise way to achieve the same thing, which is to perform different operations based on the arguments that are provided to the function. And you can see the output is again the same with the same values. Cool. Some machine learning example. In this case, we will explore the Titanic example, which is a very common example for machine learning. So it starts out with information about the passengers on the Titanic. It includes, I believe, their age, their gender, and which class they traveled in. So whether first class, second class, or third class, and ultimately whether they survived or not. And the idea is you use that simple data set to train a machine learning model that you can then ask questions of in terms of if there was a passenger who was 40 years old and was traveling in first class and was male, how likely is it that that person would have survived based on the data that we have? Very typical kind of beginner machine learning example. So this is how we do it in Python. We, the idea is we train a simple classifier that is just fed the Titanic data, basically. And once we have the classifier, as I mentioned, we can ask different questions. So in Python, we can use pandas for some data frame manipulation, NumPy for numerical computation, OS for some basic operating system level functionality, and CSV for learning. For importing CSV files. And finally, sklearn linear model we're using for the actual machine learning model. The first thing we do, we go to the directory where our CSV file lives. We're using pandas to read that CSV file. We're dropping all missing values and so on. And then the rest of the code here in Python is just very typical kind of data cleaning and machine learning pipeline. So let's run this code and let's see what we get. So here we get just some summary information. So this is what our data set looks like. We have the ID of the person. We have which class they traveled in, what was their age, what was their gender, and whether they survived or died. And then finally, the last thing we want to do is provide some values to the model after it is trained and see what the probability of survival and death is for those values. So we're passing these values and we're asking what is the probability that that person survived. Well, that's 0.86. What is the probability they died? That's 0.13. So a fairly standard machine learning classifier. Now that classifier is not going to be incredibly good because we're using that Titanic data set. Obviously, there are only, I believe, a few hundred people on the Titanic, so it's not really a massive data set. Typically, when you're training machine learning models, you would need larger data sets. But this is good enough for some kind of examples. So here is us doing the same thing in Wolfram Language. So we are importing the Titanic CSV file, and we are using the classify function in Wolfram Language, which basically is kind of a super function that that is able to take data and without you having to specify every granular step, every method, every parameter possible. It aims to give you some sensible defaults and accomplish the task, which is to produce a classifier. So let's run this and let's see what we get. We get a classifier function at the end of it. And there is one important point to make here, that if you were somebody who is deeply familiar with machine learning, and you do want to specify every single parameter and every method and every possible configuration to the classify function, you could, but you don't have to. So but if you did want to, the documentation lists pretty much everything that you can specify for the classify function, decision, top probabilities, and so on, different things. But one of the kind of philosophical differences, if you will, in Wolfram language is that functions should have sensible defaults and sensible heuristics for kind of determining what is the most, given this data, in this case, given the Titanic data, what what are the most sensible defaults to produce a classifier function. So if you're somebody who is just exploring the data, you can use it without needing to be really an expert in machine learning. And then once we have the classifier, we can do the same thing. We can provide some example values, and we can ask our model, based on your training, predict how likely it is that a person who traveled in the third class, um, who was age 23, male, give me the probability that they died or they survived. And for this person, it's our model is saying that there's 78% chance that they died and 21% chance that they survived. So if we switch their class to first class, actually there's a higher probability that they died. So I wonder what our model thinks gives people a better chance of survival. Maybe age, not really. Maybe gender. Yeah. So if you're traveling in the first class, and you're a 55-year-old female, then our model thinks that you have a huge chance of survival. Um, Again, as I mentioned, because we're training these things on very little data, they can be kind of skewed. But again, very useful for kind of playing around with data and quickly iterating on some ideas and so on. And you can get more information about the classifier here. What is the accuracy, what classes there are, what method was used. So in this case, random forest was used, which can probably explain why our model has some weird outputs, and some other kind of metadata information about the model. Cool. Just a few words on how to use Python from Wolfram language before we move on to the other side of the story. So these external language cells you have already seen from some of the previous examples. And these external language cells allow you to evaluate code from different languages. There are quite a few built-in built-in external languages in Wolfram Mathematica. So you can execute Python code, R, Julia, Octave Java, Ruby, and so on. For the purposes of this example, obviously we are interested in Python. So open up an external language cell, set the language to Python, and inside you can have all of your Python code, just as if you were writing in a Python just as if you're writing in a Python environment. Execute that cell, and then you get your Python output. There have been a lot of efforts recently to make the whole working with Python pipeline very streamlined. So I believe this should work. These external language cells specifically should work even if you don't have Python installed in your machine. It's just that the first time you run them, a Python environment will be created, a runtime will be downloaded, and basically all of the setup steps needed will be done kind of behind the scenes. So from the user's point of view, you just write your Python code and you get your Python output, and that's it. The more manual way of doing that, the same thing, evaluating Python code in Wolfram language, is to use the external evaluate function. And really it is these external language cells use external evaluate behind the scenes, but there are a few reasons why you might want to use external evaluate yourself. But let's look at a simple example. First, we're using external evaluate. We're specifying the language we want to use, in this case Python, and then the second argument to the function is all of your normal Python code. So again, here inside the second argument, you just write your Python code as if you were in a Python environment, and you get your results out. One reason why you might want to use external evaluate over a normal external cell is that you can combine Wolfram language and Python code together. So you can see here we're using external evaluate. Again, we're specifying that we're using Python code. And in the second argument, everything you see here is Python code except this little piece here, which is actually Wolfram language code. So we can test this by running it in a different cell. That just gives us the number 10, the integer 10 as a string. Because fundamentally any code that we send to the Python interpreter is just text, we can combine normal Python text with any Wolfram language code that produces the text we need. So normally if we were writing this in Python, we would say list equals np range, quotation mark 10 and close quotation mark. But just to show you that we can kind of inject Wolfram language code in these external evaluate calls, we are joining strings with Python code, Wolfram language code, and again, finishing up with Python code as well. And that works just as you would expect it to do. So yeah, one reason to use external evaluate over external language cells is to be able to kind of inject code into your Python expressions. Because if this was in an external language cell, let's test just for demonstration purposes. If I included that in a Python cell, then the external language cell tries to interpret everything as a Python code, and obviously this little piece here is not Python code. So let's see what happens when we run it. Let me just fix the syntax a little bit. So yes, it's telling me that arange, the numpy arange function doesn't accept this type of argument because it doesn't recognize it. Obviously, numpy doesn't recognize Wolfram language code. Cool. The good thing about external language cells, though, is once you define a variable, once you store something in a variable, it persists for your whole Wolfram language session. So if you store something in the list variable, just like we did here, we stored range 10, which would be the numbers from the numbers from 0 to 9. We stored it in the list variable. So then later on, if we want to get that list from another cell later in our Wolfram language notebook, it persists. So and that persists until you quit your Wolfram language kernel. So either until you quit Mathematica entirely or until you evaluate something like this quit option, and then list is not defined anymore. I'm just trying to evaluate this to see what error we're going to get. And yeah, so it's basically an undefined function because we quit the kernel. This is the same as just closing Mathematica and opening it again. Cool. A few more things I want to mention before moving on to our Jupyter notebooks is we can store the results of external evaluate calls in Wolfram language variables. So in this case, again, let's look at what we have here. So we have this external evaluate, we're evaluating Python, and we are generating some data, basically some numeric list data. But now, crucially, this whole expression, this whole external evaluate call, we are storing the result of it in this Wolfram language variable called numpy integer array, or numpy int array. So let's run that. And once we store the result of some Python code in a Wolfram language variable, we are able to use it just as any other Wolfram language variable, really. So we can do normal on it to see its full structure, or we can apply some function to it. Once we have it in our Wolfram language variable, then for all intents and purposes, it really is just a Wolfram language expression at that point, even though Python was the interpreter that generated that expression. There are some nice kind of conveniences, one of them being that for some common Python specific data types can be imported directly into Wolfram Language, so they can be stored in Wolfram Language variables directly without needing to convert them to something else. So in this case, we are looking at NPy and NPZ files. So these are data types that are generated by the NumPy library in Python. And typically, if you are trying to export into some external language, you would have to do the conversion yourself. But because they're such a common data type in Python workflows, then external evaluate knows about them, and they can be stored in Wolfram language variables in the same way. I believe this is also supported for some pandas data types. So pandas is again another very common data analysis package in Python. So for the very common ones, you will find that you are able to store them directly in Wolfram language variables. Um, but it's important to say that that's not going to apply to every single um, one. So if you have some kind of niche Python library that produces some custom data type, chances are you're not going to be able to transfer it as cleanly between Python and Wolfram language. But if you're working with the big ones, NumPy, Pandas, and so on, then it should be fairly straightforward. Cool. There's one more thing I want to show you before I move on to. I'm just seeing if it's in the slides or if I need to write it live. Let me just grab the example from documentation. So this was added in one of the more recent versions, which is why I want to show it to you now, because it does make some Python workflows quite a bit easier. Let me just copy and paste this in a new cell. So this function, start external session, you can use that function to start a kind of provisioned Python virtual environment that contains only the packages that you need it to contain. So you can see that in the previous examples, we have been using different packages, NumPy, SymPy, Matplotlib, and so on. So the reason these work immediately is because I have these packages installed on my system, and they're available for any Python environment that runs on my system is able to use them. But a lot of times with Python, you want to define an isolated environment where you can specify exactly which packages should be included, and then everything else is excluded. And that's important because it avoids a lot of problems that occur in Python when you have two different packages relying on the same common package, but they need different versions of it, and then you have version conflicts, and they're very painful to resolve, and so on and so on. So typically, the kind of the Python way of dealing with that problem of preventing it from happening in the first place is to create virtual environments, and that's exactly what start external session allows you to do. It allows you to define, to start up a fresh virtual environment for your Wolfram language session, and you can specify exactly what should go into that virtual environment. So in the example that we have here, we are starting an external session with Python, because you could do that with other languages as well. And we are saying that the packages that we want included in that virtual environment are emojis, or just a single package in this case, but it could be other things like NumPy, SciPy, and so on. We have an environment name, so we can refer to it directly in our code, and we can even specify the version of Python that we want that that external session to use. Again, there are some packages that don't like some Python versions, either because they're too old or because they're too new. So if you know exactly which packages you're going to use, you know exactly which Python version you need, you can specify all of that information beforehand, and that prevents you from having any issues down the line. And once you start this session, you can there's some I was Yeah, I was messing with some settings just before the environment, so this is not going to work. I need to fix that, but I can show you what the idea is. I was trying to be clever with the start external session, and I'm not really, and I broke it a little bit. But this is going to work on your machine if you test it right now. Um, Once we have our external session, we can just pass it to external evaluate, and then any Python code that we pass as the second argument is going to be evaluated by this specific external session, rather than your system-wide Python interpreter. Which in this case, I believe it's not going to work because my session needs to be fixed, but that is the idea. Again, that's it's a very common, very useful kind of workflow that you can employ in Wolfram language to kind of keep your Python environments isolated from each other. It really helps in the long run, even if you think that you don't need it because you're just doing one thing. And from my experience, just one thing leads to another. Before you know it, you have this huge code base, and then you hit your versioning issues, and it becomes a nightmare. So it's a very good practice to for every workflow you have. Um, start um, Start an external session, define your dependencies, come back and add more if you need to. And these virtual environments are very lightweight. Um, they're very easy, very quick to start up, so you're not really paying any cost other than having to write this piece of code yourself. But if it saves you trouble down the line, then it really is worth it, in my opinion. Cool. I believe this is all we had to talk about on the Wolfram language side. Hopefully that gave you some idea. Oh, really? We started with a broad comparison between the two languages. Hopefully you have some idea um, of what the main differences are, both in technical terms like syntax and control flows and so on, but also in terms of philosophy. What is what is the kind of most convenient way to use Wolfram language? What is the most convenient way to use Python and so on? And then later on, how do you actually use Python from Wolfram language? So typically, external language cells one way, external evaluate the kind of more programmatic way, and start external session to kind of provision your own isolated environments. Um, so yeah, I think that's it from the Wolfram language side. So let's move on to Python world. Um, Let me just open. Let me see if there's anything else to mention before I open our Jupyter notebooks. Um, yeah, there are some other examples here about things that Wolfram language is especially good at compared to Python. Um, but I'm not going to go through every one of them because we don't really have the time in this webinar. Maybe this is worth mentioning. Every time you want to do some interactive elements where you have some functionality and you want to provide some user interface to that functionality, that's very typically very easy to do in Wolfram language, and it's a bit painful um, in Python. Although that's probably not the good example, not the best example of that point, because this does look fairly complicated, to be honest. But typically for kind of interactive, manipulatable elements, Wolfram language does give you this manipulate. Again, what I would call a super function that is able to do a lot of different things based on the input. So that's one thing where Wolfram language is pretty good at. Some web stuff, yeah, that's pretty much it. Let's go to the Python side, and we have half an hour to see how we can use Wolfram language from Python. Let me zoom in a little bit because this is probably way too small to see. Where is my zoom in? Zoom in. Okay. Oh, that's too much. Okay. All right. So if you have, it's just testing a few things here as well. Okay, so if you have downloaded the materials for this webinar, which they are available, by the way, at the top of the chat on Big Marker, and they're pinned in the chat on YouTube. So if you have downloaded the materials, you have access to several Jupyter notebooks, as well as the Wolfram Mathematica notebook that I showed you in the first half of the webinar. But this is the first of the Jupyter notebooks that we're going to cover, and it's about the basic Wolfram language integration with Python. So we are going to be looking at how do we define. So once we live in a Python world, so to speak, once we live in a Jupyter notebook, where the idea of the notebook is still the same. We're combining normal text narrative with some programming code and outputs. But in this case, the programming code is obviously Python. So once we live in an environment where our main language is Python, how do we use Wolfram language code from that environment? So this is all that this and the next few Jupyter notebooks are going to be about. So let's get into it. The main way, just on a high zoomed out level, the main way we use Wolfram language code from Python environments is by making use of the Wolfram client external library. So you can see already very much in the spirit of Python, calling an external library and doing something with it. In this case, this is the official Wolfram language for Python library, again maintained by the same people that maintain the language, and it provides a really nice interface from Python. So the first thing you need to do is obviously install the external library, and then we can start using it. So let's see what is happening in our Python code here. Importing the Wolfram client language, and we're importing a few specific symbols. I'll tell you what the difference is between those as we walk through the example. In the first example, we'll focus on this WL symbol. So the WL symbol from the Wolfram client package is used to represent any built-in Wolfram language expressions. So let's look at our code here. So we have a variable, and we are using WL to define a few Wolfram language expressions. So we have WL select, which corresponds to the select function in Wolfram language, and then we have two arguments that we're passing to the select function. We have again a Wolfram language function called range, and we have 10. And then the second argument to the select function we're passing is this prime q function. So I think it actually might be helpful if I write that out in kind of typical Wolfram language code, so you can see what the difference is between the syntax. So let me just bring a Wolfram notebook on the side here and write the same thing if I was writing it in a Wolfram notebook. So we have select, range, 10, and then we have prime q. So basically, if you want to write this piece of Wolfram language code in Python, this is the way to write it. For every built-in function, you basically prepend it with WL, and then the function name. Cool. So we are defining a few functions, and we're storing them in some Python variables in this case. The first, I just show you what it looked like. The second is, again, a very simple function using reverse and using range 10, which will basically give us the all the numbers from 1 to 10 in reverse order. And then finally, we have now, which gives us the current time, I believe. So let's evaluate that in our Jupyter notebook and see what we get. You'll see that we get the formalized Wolfram language code, so what I just showed you in the Wolfram notebook for all three functions. But you'll see that they were not actually evaluated at that time. And that's because Wolfram language allows you to define Wolfram language code, but if you want to evaluate it, you need to evaluate it against a Wolfram language session, which I'll show you how to start that. And how to evaluate Wolfram language expressions. But for now, we are just defining some Wolfram language code in our Python environment, and we are storing that Wolfram language code in a variable. So the Python variable x from now on is going to carry this piece of Wolfram language code. At the moment, it's not evaluated. It's just an expression that we are storing. The other function that the Wolfram client package provides to you is WL expression, and that's very similar to the WL one. But with WL expression, you can prepend to any custom any function in Wolfram language that you have built yourself. So any function that is not part of the built-in functions in Wolfram language. So you can see in the previous example, all of the functions we were using, select, range, premq, all of them already exist in the language. So we just use WL. Here we are defining a pure function, which basically says that we are going to square each argument that goes into the function. But that's not a built-in function in the Wolfram language, so we're prepending it with WL expression. Map, on the other hand, is a built-in one, so we're prepending with WL. So basically what we're going to do is we're going to map this custom function that we have that's going to square everything that goes into it. We are going to map it to each one of these arguments, 1, 2, and 3. Again, evaluate the cell, and that stores our Wolfram language function but doesn't execute it. All right, how do we actually start executing the functions that we have stored? So again, using our Wolfram client external library, we are importing Wolfram language session. And that is what is going to allow us to actually evaluate these expressions that we have been storing so far. The first thing you need to do is you need to start a session. So typically, you can start a session by just calling this Wolfram language session function without providing any arguments. So this should work on most machines. If it doesn't work, if it says, because what the Wolfram language session function tries to do is it tries to locate an installation of Mathematica on your own machine. So 9 times out of 10, it is able to do that automatically. If for some reason it fails, like it does on the machine that I'm presenting from now, what you can do is you can explicitly pass the location on your machine of the Wolfram language kernel. In the case of the machine that I'm presenting from today, it is in C program files, Wolfram Research, and so on, until we get to the Wolfram kernel. And that's important because this Wolfram kernel is what is going to be used to evaluate the Wolfram language expressions. So I see that Jorn in the chat is asking, how is the license evaluated when using the Python package for Wolfram language? And that's exactly the way. So you are pointing you're pointing to the Wolfram kernel installed on your machine. So whatever license is associated with that is the license information that is going to be used from Python. And you can think of Mathematica as doing the same thing. So Mathematica is the kind of the front end, the IDE, if you will, for the language. So it allows you to write code, but the actual code is being evaluated by the kernel too. So yeah, all license information associated with your Mathematica will automatically be inferred when you use the Wolfram kernel in this way. Cool. So once we define the session, we store it in a variable, and then we can call the evaluate method on that variable, and we can pass all of our stored Wolfram language expressions. Let's test that again, make sure I got the path right. So in this case, we are evaluating the x variable using the Wolfram language kernel. And just to remind ourselves, the x variable was this specific Wolfram language function, which was this Wolfram language function. So it gets the numbers from 1 to 10, and it checks those. It only gives back those that are primes. And you can see the result. It's 2, 3, 5, and 7 are the primes. And you get some metadata about the result. It's integer 8, it's a packed array, and so on. Let's evaluate the other Wolfram language functions that we stored in variables y and z. And again, the Wolfram language function that we stored here was reversing the numbers from 1 to 10. So you can see that in the result, and function that we stored in Z was now, which gave us the current time and date as a Wolfram language date object. So again, you see that even though the kernel is able to evaluate the function, Python doesn't know anything about Wolfram language date objects. So if you were running this in Wolfram Mathematica, you would get a nice kind of output that just tells you the current date and time. Because Python doesn't know anything about Wolfram language date objects, obviously, you just get the full form of that output. But in any case, once you get the once you get the output out in Python, again, you can treat it as any Python variable. You can store it in its own variable. So maybe you can call this Z output. You can store this in a variable, and then you can operate on Z output as if it was any other variable in your Python environment. So let's do some kind of more complicated operations using Wolfram language from Python and kind of mixing and matching both languages. So here we are defining some data, some numerical data in Python. So this data line that you see here is just a Python list, all Python syntax, no Wolfram language. Then we want to define some graphic, and we want to use Wolfram language to define the graphic because a bar chart provides us some very nice visualizations by default. So you can see that the first part of that expression is a Wolfram language function bar chart. The first argument we pass to that is a Python expression, and then we finish off with Wolfram language syntax. Then we move back to Python. All of this is Python code. We're just defining a directory where we're going to export the graphic. And then for the actual export, again, we are defining a Wolfram language function. Export, it takes a Python expression, and it finishes off with some Wolfram language arguments. So you can see that in the same cell, in the same piece of code, you can really mix and match very easily both languages to get what you need. So all this little piece of code does is it generates a bar chart, and then it exports it as a PNG file in some specific directory. So in the next cell, we are going to import that image back to our Python environment, and we use PIL, which is by far the most common library for working with images on Python, and this is just pure Python code. There's no Wolfram language here. We just use Wolfram language to generate the graphic and export it to a directory. Once we have it exported, then we can stay in Python world and just import it, and visualize it, and do whatever we want with it. Here again, we are operating on a similar kind of graphic that we're going to export with some filter, some gradient filter on the image with some parameter 3, and then the same thing, export it and then import it from our Python side. Cool. So the last main thing I wanted to touch on in this Jupyter notebook before we move on to the next one is functions. So up until now, I showed you how you can use built-in Wolfram language functions just by prepending them with WL like this, and how you can use your own custom Wolfram language expression by using WL expression. And I showed you how you can kind of mix and match Wolfram language and Python code. So really the last thing we in terms of basic things that you want to do with code with both languages, the last thing we need to cover is functions. There are a few different ways you can wrap Wolfram language functions in Python functions, and they are, for all intents and purposes, they are equivalent. So which one you choose really would depend on your kind of really on your preference. The first one is actually my preference, so let's look at that first. So the way we can use essentially a Wolfram language function and store it in a Python function is we define our Python function at the beginning. So we're defining a function with the name population density, and which takes one argument, which is country. Now, this is Python syntax, and what we want to say is that this Python function will return the result of some Wolfram language logic. So all of everything inside the return statement is, as you can see, Wolfram language code. So that's a very convenient way of wrapping Wolfram language functionality in a Python function. Because again, once you define the function, once everything is fine, you can use it just as you would use any Python function. You just call it on the top level, you provide the argument, you get the result. Really, if you didn't see the definition of this function, there's no way for you to tell whether it's a Python function or a Wolfram language function. If you're just calling it by the function signature, you get the result. You don't care. Another way to really accomplish the same thing is to wrap a whole Wolfram language workflow syntax inside of a W language expression. So again, it's basically as you're you're defining, in this case, you're defining a Wolfram language function. You're using Wolfram language code. There is no Python function happening here. You're just using session evaluate. You're using Wolfram language expression to indicate that this is going to be a custom function and not something that already exists in Wolfram language. And then inside is just pure Wolfram language syntax. So here the function definition is in Wolfram language syntax. This is the name. These are the arguments. And this is what it does on the right. And yeah, once you have that, you can call it with session function. And you can use the name of the Wolfram language function as an argument to the session function call, and that really gives you the same result. So it really depends on whether you prefer writing Python functions, in which case you would use this first kind of way of doing that, or if you prefer writing Wolfram language functions, in which case you can just define it like this. Cool. One last thing to mention. As you saw, we to evaluate Wolfram language code from Python, we started our own session. That session doesn't terminate automatically, so it's always a good practice to terminate the session whenever you're done with it. Because if you don't, even if you exit VS Code, that session is going to keep running. It's just an empty process on your machine. So it's always a good idea to terminate that when you're done with your workflow. Another way, a very common way of handling those situations in Python is to use this with block syntax. So with everything that goes inside the with block syntax is evaluated, and once that is done, then this Wolfram language session is terminated automatically, so you don't have to do it manually. But yeah, same idea, whether you terminate it manually or whether you use it with a with block, so that everything is so it's terminated automatically. It's basically the same idea. Cool. We have time to, let me see we have 10 more minutes. I really want to go through probably through the fourth notebook, because it actually looks at some actual example that combines both languages. So the second and third Jupyter notebooks, if you're trying to follow with the materials for today, the second is all about serialization, which is about converting data types from one language to another. That's very useful if you are dealing with custom types. You really want some um, automatic conversion pipeline happening. There's a lot of information about that in the second notebook. And the third one is actually um, using a cloud evaluator instead of a local evaluator. And the main advantage of that is that you don't need to have a Wolfram language installed on the machine that you're running the code. You can still use cloud evaluation. And to go back to the license question, as long as you have a Wolfram language license, you can generate these secured authentication keys. The ones you see here are just an example. They're not going to work. But if you log into your Wolfram language account, you're able to generate these key pair. And then that's how you authenticate yourself. That's how you can say, I have a license for Wolfram language. Let me use it from Python. And again, the advantage of that is that you can run Wolfram language code on any machine that you want. Any machine that can run Python, you can use that to kind of authenticate yourself. And really, syntax wise, once you start the session, you start the session using slightly different syntax. So obviously here it's Wolfram Cloud Session instead of Wolfram Session. But once you start the session, everything else you do is pretty much the same as it was in the local example. It's just that in this case, it's an actual cloud machine that evaluates your code and not your local machine. So depending on what you're trying to do, cloud evaluation might be something that you're interested in. Cool. So then the fourth notebook tries to look at a practical example of Wolfram language with, I don't know why it says cloud, because I believe all of this example is a local example. Let me just have a very quick scan through the code. It does say cloud. There's nothing cloud happening here. It might as well have been if instead of Wolfram language session we used a cloud session, then everything else below is going to work. But in this case, because I don't have the authentication keys for my account at hand, we're going to use a local session. So let's do that. And let's look at what we are trying to do here. So the first thing we need to do, obviously, start our session, because that's going to evaluate all of our Wolfram language code. So first thing we do, start a session, store it in the session variable, which we're going to use later on. So the next thing we're going to do is we are working with a CSV file that, again, you're able to find in your in the webinar materials for the session. But it's just a CSV file containing information about the GDP of all the countries in the world. So here is kind of the head, so we can get a feeling for the structure of the data set. We have all of the countries here in the first column, and then we have for each year between 1960 and 2021, we have the GDP of that country. We have a lot of missing values that you can see, which we are going to sort out in the next step. So here we're just doing some data cleaning. We are dropping some columns that we don't want to use, indicator name, indicator code, country code, and so on. We are also removing the world. The world is listed as a country in this variable, which we don't want, so we're dropping that. All of that is done on Python side, by the way. We haven't brought in any Wolfram language code yet, so all you're seeing here is a Python syntax. Now we can look at what our data set looks like after the rough cleaning that we have done. So now we just have the country name and all the years that we're interested in. So here's where we bring a piece of Wolfram language code, which is we are defining a function called pop that is going to take 2 arguments. And it is going to return a population for that country for that year. So it's a function that takes the country, let's say the UK, and it takes a year, let's say 2015, and it's going to return the population of the UK for 2015. And the main advantage of doing that in Wolfram language really is that again, as I mentioned previously, we have a lot of that information already built into the language. So you could do all of that in Python as well, but you would need to source that information from elsewhere, either from the web or from some source that you trust. Whereas with Wolfram language, you can just query that in the language itself. So let's define our Wolfram language function and let's test it with a few different inputs. So here we are passing it the UK for 2010, and we're also passing it something that is not valid, in this case not a country, for 2010. And ideally, hopefully, this should return the first argument. The first call should return an actual population. I wonder why it doesn't. Interesting. Let's try with a more recent year, maybe. Maybe that's the issue. Oh, I need to see what's wrong with the function, but typically when you pass it a normal country and you pass it a year, it should query that and give you the population correctly. I wonder if the rest of the example is going to work, if there's any issue with that. So let us test. Yeah, there's something wrong with the function. It's giving us not a number for each one of them. There's probably, let me see if there's anything obvious that I can spot in the Wolfram language syntax, which is making it not work. But if not, I can just give you the idea of the example and explain what it would do if it worked. So we have these. We're interpreting it as a country. I wonder if there is some issue with our network. Again, let me just do a quick test in Wolfram Mathematica. I'm not going to spend a lot of time debugging. If it doesn't work, it doesn't work. But I wonder if there is an issue with the network. Because earlier when I was trying to show one of these examples, it didn't work. So let's see. So every time you query the Wolfram language knowledge base, a request is sent to the Wolfram language server, which send you the response. So sometimes when there are network issues, you can have these problems. Although it seems to work fine in the I really want to test it now. It seems to work fine in a notebook. So if we have population UK, and then we have 2020, what is that going to do? It works fine in a Wolfram notebook. I wonder why. Did we start the session correctly? Let me just, I'll just spend an extra minute trying to debug this because it is bugging me a little bit. I wonder if it's because of the session. Because this really should work. So let's try starting a session with an explicit path and then run everything now. See if that does it. Yes. Okay, so the problem was that at the beginning, as I was mentioning in the first example, I started a Wolfram language session without a path. And on this machine, for some reason, it's unable to locate where my Wolfram kernel is. But once I start the session with the correct Wolfram kernel, then I get the expected output. I was wondering what was wrong. Anyway, to go back and to wrap up this example, because we are running out of time, to go back to the example that we were looking at, we are passing in the first case, we're passing France 2020, and we get the population. When we pass something that is not a country, we're getting not a number, which is expected. So the next thing we want to do once we have ensured that that all of our code is working correctly is to apply the function to each row of the dataset, replacing all of the GDPs with population. So as I mentioned, every time you do one of these Wolfram knowledge base requests, it has to go to a Wolfram language server, and you get the response back. Because we are doing it for quite a lot of countries here, we're using a Lambda function to do it for every single country in our dataset. This is going to take a little bit of time. Hopefully, it should wrap up in a few seconds. There we go. And then we're just returning the final value. And then it's still failing for some countries. I wonder why. Oh, in any case, I think it's an interpretation issues because we're passing the countries as strings. Maybe the interpreter is failing at interpreting Africa, Eastern, and Southern as a country, for example, which makes sense. And then finally, what we want to do is to plot the population of one specific country. In this case, it's Aruba, but it could be any of the other countries in the dataset, using again a mixture of Wolfram language and Python. The main function that does the plotting is Wolfram language, and then the rest of the workflow here is Python. And this is what you get at the end. Again, we are creating the final plot in Wolfram language. We're exporting it, and then we're importing it from Python. So this is what you get at the end. A nice enough plot that shows how the population of Aruba has changed over time. So now essentially what we have done is we have augmented our dataset, which at the beginning only included the GDP of the countries. Now we have augmented it with the population. We can query other properties of the countries. So if I go back to my notebook, I can say Aruba country, just so we can see what information we have built in for that country. So if we pass the properties key, we are able to see. Let me make this a bit bigger. So all of these things are things that are built into the Wolfram language. So you can augment your data sets with them and do different types of analysis, whether you want to stay in Wolfram language or Python. It's entirely up to you. But this is a simple, just a simple example of, again, how you can combine both languages, this time from a Jupyter notebook rather than a Wolfram language notebook. So depending on your preference, depending on your style, depending on what you like to do, which language you prefer writing, you would choose one or the other. But hopefully this webinar has given you enough of an idea of how the two languages are similar, how they are different, and ultimately how we can combine them in the same environment, whether that environment is Wolfram language notebooks or Jupyter notebooks or some other type of notebooks entirely. As long as you have access to Python and you're able to import this external library, then you are able to use Wolfram language code. So that's it for today, I believe. So I'll just hang around for a few seconds just to see if there are any questions. And if not, thank you all very much for attending, and I hope you have a lovely day.